confused. I mean, I need to internalize this again. X minus A and A closure, right?
Yeah.
Closure of A.
Yeah. Yeah.
They seem to be very, there seem to be a kind of, I think in some certain cases when A is closed, right?
When A is
When A is a closed set,
Hmm.
right?
Hmm.
And essentially what is happening is, uh, the uh, um, A and A and its closed set becomes same, right?
Okay.
So there is, I'm little confused between X minus A and A bar, right? Essentially, they seem to be very almost same,
Oh,
except for the
no way, no way, no way, no way.
I
A bar, actually, unfortunately, a lot of people use different notations. So
right,
usually,
that,
probability, A bar is the complement of A.
right. That's
So
why.
that is not the notation we are using here.
ఆగు.
A
నేను
bar is
ఓవర్
intersection.
ఇస్తాను. ఓవర్ కావాలి నాకు. ఎవరైనా ఏమైనా ఇస్తారా? I can give 2 woods, 2 bricks.
Hey, Rohit, you can go on mute. Rohit, you can go on mute.
Rohit is in there.
Oh, okay. Yeah.
Is Rohit?
Yeah, he joined.
Okay.
Yeah. He's talking to someone else.
See, A bar is intersection of all the closure sets that contain A. So from out above A, we are looking at lots of closure sets and their intersection is A. So in some sense, A bar is the smallest closure set that contains A. X minus A is totally something different, right?
Right.
So if, today I will make sure I give you some examples of standard sets where we find closures and things like that. Maybe we should just get ourselves familiar with the number line as well as the complex plane. We'll do that today. I think I will do some examples.
I think this notation is that the closed set of A is used as A bar, because some of these things are little intuitive, because the way the notations that I was using, like A union B bar of A union B, because as soon as you think about bar, it's kind of a complement set. So I'm tend to think that X union B, A union B bar is A bar intersection B bar, because if you think of bar notation as a
No.
complement, so this is where that confusion is coming from.
So I have a topological space. I'm just going to revise that. XT
Yeah, it's good.
be a topological space, right? For any subset A of X, A bar is intersection of all closed sets F. A is contained in F and F is closed. That's what your A bar is. And I have shown you that A bar is smallest closed set containing A. Containing A. That's what we showed. We'll take examples. And also I have proved in previous class that in a topological space, X naught belongs to A bar if and only if for every open neighborhood G of X naught,
Hello.
for every open set G that contains X naught, G intersection A is non-empty.
Hello.
Okay. So, for example, if I look at my complex plane with the
Hello.
E,
Hello.
say I have taken some region like this. One can imagine some region like that I have drawn here, right? You can see every point over here on the boundary be in the closure of C. Maybe I can, as an example, I take my uh,
Hello.
A to be B 0 1. So circle with center at 0 and radius 1. Can you hear me? Okay.
There's quite a lot of an echo. I can hear you, but there seemed to be quite a bit of a echo.
Oh, quite echo. He's adjusting that.
Okay.
He will do the adjustment. Now,
Okay. Now it looks okay.
now you see, if you take any point on the boundary, boundary has to be defined very carefully in topology. But if you, a layman will say that is the boundary of the disk, right? This is the open disk. I've taken all the points in the complex plane whose distance from 0, which is mod z, is less than 1. Now, if you take a point on the boundary right here, right, which is whose distance from the origin is exactly 1, and you see that every open set I can take around, okay, is going to intersect this set in some more elements, isn't it? That's why that point on the boundary must be in the closure of A. Instantly, maybe I have to do this also. See, when you look at the metric topology, C with D, okay, this metric topology is generated by the following as the base. The base is set of all balls B, Z0, R, where Z0 is in C and R is positive. Okay, so it's generated by this. What do you mean by generated by this? That means the open sets in C are going to be arbitrary unions of basic open sets. So G subset of C is open if and only if G is a bunch of union open balls. G is union.
We cannot hear you anymore. I think some issue with the audio. We cannot hear you anymore. If you are able to hear us. Okay.
R greater than 0 such that x naught is in B, x naught R is contained in G. How can the set G be open? For every point inside G, I should be able to squeeze in a little ball.
We have some audio issues.
It's not audible?
Oh, yeah. Now we can
no.
hear you.
It is
Go
fine
ahead.
now?
It is fine now. Yeah,
So
go ahead.
what I am saying is that first of all, I have to understand the topology in C before I explain those things. So this collection of all balls it will be a basis for this topology. That means the open sets in C are nothing but unions of such balls. And therefore, how can something be open? If for every x naught in G, I can squeeze in a ball around x naught contained in G. So for every x naught in G, I squeeze in a ball. So here is the G. How can this be open? No matter whatever X naught I take in this, I will be able to squeeze in a ball around that inside G. Another X naught, a ball around it inside G. Another X naught, ball around it inside G. That means all those balls, actually their union will be G. So for me, a set G, a subset G of C is open if and only if for every point in that subset, I'll be able to squeeze in an open ball which is contained in that. So if I go back and talk about this theorem, X naught in A bar is closed if and only if for every open set G containing X naught, G intersection A is non-empty. So I can replace this, instead of saying for every open set, I can say for every R greater than 0, the ball B X naught to R intersection with A is non-empty when you come into C. In topology, I don't have balls. In topology, I have not introduced any metric. But in metric, I can actually replace this closureness X naught in A bar if and only if every small circle I take around that X naught, that circle intersects this set A. So that happens even for a point inside here. For a point inside doesn't matter. You can always draw a small circle which is contained in completely inside that. So that intersection A is non-empty. So in addition to the points inside, I'm also picking up points on this boundary into my closure. The closure A bar is that. The closure A bar is actually along with the interior, the boundary that is becoming what is the closure. Am I okay with that?
Yep. Yeah. Makes sense.
Okay. I will maybe give you a bunch of examples one by one. Let me just go a little further and then come to that. Let's go to the next place. Okay, next place. Well, we talked about on the other day what is a derived set is. I didn't probably explain properly. We talk about that. Okay, let X T be a topological space. Okay, usually I don't write all that. I say let X be a topological space. Okay, X comma T be a topological space. A be a subset of X. We define what I mean by limiting point of this. The definition is X naught in X is called a limit point or limiting point of A. If what? If for every open set G, okay, containing X naught, okay, we get, I think I should improve this. I'll tell you for simplicity, man, excuse me. I'll tell you for simplicity, first of all, let's use some notation here, that's better. Let xt be a topological space, okay? X naught be an element in X. What I mean by a neighborhood of X naught is any open set that contains X naught is called a neighborhood of X naught. Any open set that contains X naught, is called a neighborhood of X naught. Okay? Any open set. Somehow we want open set only. In our layman's language, open neighborhood is something around here, but I'm only looking at an open set. For example, the closed interval -1 to 1 is not considered neighborhood of 0. Only the open interval -1 to 1 is considered neighborhood of 0. Or any open set, for example, open 0 to infinite. Okay, open 0 to infinite can be considered as a neighborhood of 1. Okay, open 0 to infinite can be considered as a neighborhood of 1, right? And there is 0 here. -1 to 1 is considered, open interval -1 to 1 is a neighborhood of 0. But the closed interval -1 to 1 in the topology, you will notice that -1 to 1 is a closed set. Even though it contains 0, I don't want to call this a neighborhood of 0. So in general, in a topological space, what is a neighborhood of x naught? Just any open set that contains x naught is a neighborhood of x naught. Let me use that kind of a language from now onward. It becomes easy for us. So talking about limit point derived set. Okay, so X is a topological space. A be a subset of X. A point X naught in X is called a limit point or limiting point of A when, if for every neighborhood of X naught, if for every neighborhood of X naught in topological space in general, okay, for every neighborhood of X naught, A intersection G, every neighborhood G of X naught, okay, A intersection G minus singleton X naught is non-empty. Aha, that means G should contain other than X naught at least one element of A. That's when you call that X naught a limiting point or the limit point of A. Okay, you'll see what it means. Okay, and in case X naught is not a limit point, you call this an isolated point. If X naught is not a limit point of A, we call X naught an isolated point of A. Okay, we'll give you examples. The given any set A, dA is the set of all limit points. This is called the derived set A. This is the set of all limit points of A. Limit points of A. That is the derived set. Okay, we'll take some examples to make you comfortable. Let's talk about in R. Okay, with the usual topology. R with the usual topology. Okay, so what is the usual topology? The metric is there. Metric gives you open sets. In real line, what are the open sets? Open intervals are open sets. So this is generated by all balls centered, on R. If I take any point x naught and they want to say B x naught R, and there is just a small interval around it, x naught minus R to x naught plus R. So all such open intervals, they make up the basis for the topology in R. That means they are nothing but all open intervals. So this is open sets in R are unions open intervals in R. Okay, thus open sets in R are unions of arbitrary unions or finite unions, doesn't matter, are arbitrary unions of open intervals in R. Intervals in R. Right. So as an example, I want to take in A, maybe A is taken as Z. Let us see that. That means I have in this all integers 0, 1, 2, 3, -1, -2, forever. What will be the limit points of that? Are there limit points at all in this? You will notice that no matter what point in Z I take, Okay, no matter what point Z I take, I can draw a circle with radius 1/2 only, which contains that n. But that circle intersection A, from that if I remove the n, there is nothing. It's an empty set. I want that difference A intersection G minus X naught should be non-empty. So no integer will be a limit point of this set Z. Even any point other than that is also not limit point, because if you take any point between the two integers, I can actually squeeze in a very small interval and around it. That intersection A has all integers only. That intersection with A has no integer at all. When and there is no even that element is also not in that. When I remove, there is nothing, and that A intersection G minus X naught is empty. So no, this has no limit point at all. Okay, A has first option. A has no limit points. Is that clear, sir?
Yep.
I'll go to the next page. A has no limit points. I take the second example. A consists of, let us say, 1 minus 1 by 2, 1 minus 1 by 3, 1 minus 1 by 4, and so on and so forth infinitely many. So this is really the set consists of 1 minus 1 by n, where n itself is a natural number bigger than 1. 1 minus 1 by 2, 1 minus 1 by 3, and so on. You can see that these are accumulating in some sense. There is a 0 and there is a 1. I have taken this point and I have taken this point, this point, this point, this point. These points are in a common man, in a layman's sense, they are accruing at 1, and I will show to you that 1 is a limit point of this set. Why is 1 a limit point of this set? No matter however small interval you take around it, I think on and after a certain stage, whole 1 minus 1 by n will squeeze into that. So we claim 1 is in the derived set of A. It is a limiting point of A. Why? For every epsilon greater than 0, that 1 minus epsilon to 1 plus epsilon, I definitely will be, its intersection with A will contain plenty of elements of A. Is it not? Lots of 1 minus 1 by n. So after, because I can choose n large enough that 1 by n is smaller than epsilon, and this will be minus that point you have taken. Okay, 1 is non-empty. Why? Because choose n naught in n large enough that 1 by n naught is less than epsilon and greater than 0. Then what is this 1 minus 1 by n naught, or 1 by 1 minus 1 by n naught plus 1, and so on? Where are they going to be? They're all, okay. So you come very close, minus epsilon to epsilon, all these things are going to be within that minus epsilon to epsilon. They all belong to 1 minus epsilon to 1 plus epsilon, and they are also members of A. So this is from which if I remove 1, I don't have to remove 1, because 1 is in the first place, not in A anyway. So that is not here, but plenty of other things are there. So that minus singleton 1 suddenly has infinitely many points in it. It's non-empty. So therefore 1 is a limiting point. Okay, I hope everybody understands that. And in for example, in C, D, the common metric, with usual topology, C with usual topology. As a matter of fact, in this, I think there are no other limiting points. I think it's clear what is happening. Limiting point means something like x naught is a limiting point. Fa what? In however small an interval around x naught I take, okay, that interval will contain, other than x naught, some point from A. So lots of points in A are accruing at x naught. Many points are there in A which accrue at x naught. Okay. I was able to talk about smaller intervals in C and R, but in general in topology, I cannot talk about that. In topology, I didn't say anything about small. I can only say upset is of another thing is smaller, but making it smaller doesn't make sense unless metric comes into picture. So the topology actually changes the texture of a lot of sets, as we'll see. Well, we're not studying topology much. My final interest is to study only things inside C. Okay, in C, I want to create another example. Maybe I can just create an example. Here, I take the set A, perhaps all the complex numbers C, right? All the complex numbers in C, such that maybe the real part of Z is more than 0 and less than 1, and imaginary part of Z is also more than 0 and less than 1. So what am I looking at it? I'm looking at kind of in the complex plane, I'm looking at this square 0, 1, 0, 1. I'm avoiding the boundary. Okay. And you can see that every element on the boundary is a limit point. This is the limit point. Because no matter what circle I draw around it, other than that, there are plenty of other things inside the set A. So that's it. That's why I think every point on the boundary is a limit point. Every point inside is also a limit point, because for every point inside, I can draw a small, whatever small open neighborhood I take that, that intersection A will contain all points. Even if you remove just that point, which is the center, I have all that set is a non-empty set. And therefore, I think every point inside the, okay, every point inside the set is also a limit point. Okay, I hope you understand what I mean by limit point. Is that okay? Any question? Good. This is very good. This set Z I have given you in the previous example, unfortunately, has no limit points at all. Okay. All right. So one small theorem I would like to do, or a proposition I would like to do, a theorem is the following. Okay. X is a topological space and A is a subset. For a subset A of X, two things happen. One, A bar is equal to A union the derived set. Okay. Actually, the derived set doesn't have to be the boundary. It can have points inside also. But once you take the derived things, all the limit points are also included into that. That becomes the closure. Is that okay now?
Yeah.
Two, a set is closed if and only if the derived set is inside A. I think it's clear now. Oh man. Okay. Okay. That's the thing. Is it clear to you now? You can able to see that?
Yeah.
Yeah. This is the whole point. So what happens is when you're talking about a boundary, the situation is like this. You have a set A. You're going to look at A bar as well as X minus A bar. Their intersection is what I called boundary of A. Outside's closure will encroach this line. Inside's closure will also encroach this line. And their intersection is just the boundary. In the usual C, it is clear what I am talking about. Okay.
I have a question. So actually, in this second point, A is closed. Okay, is this like a condition when then only we say it's closed, right? I mean the second. Yeah, I'm sorry, I got it. Yeah.
We'll see. I couldn't hear you well. Anyway, so I probably I don't need to prove this. It's kind of obvious now. Okay. Uh, anyway, if I want to prove, here is a proof. To start with, the A is contained in A bar. That much we know already. So if the dA is contained in A bar, you have to say that. So if I take X naught in dA, the very definition says that for every neighborhood G, that means any open set G that contains X naught. You already know G intersection A minus X naught is non-empty. Already we prepared a theorem. Even if G intersection A is non-empty, I don't need G intersection A minus X naught is non-empty. Even if G intersection A is non-empty, you are saying that for every neighborhood of X naught, G intersection A is non-empty. So X naught belongs to A bar. This implies, okay, for every neighborhood G of X naught, A intersection G is non-empty, which implies X naught is in A bar. So both A is contained in A bar and dA is contained in A bar. Together it says that therefore dA is contained in A bar. So I think we have proved one side of the result. Thus, A union dA is contained in A bar. You have to prove the other side. I think you can understand this. On the other side, suppose I took an X naught in A bar. That X naught I have taken in A bar is either in A or in dA. Suppose X naught is in A, then I show X naught is in dA. Suppose X naught is in A bar. If X naught is not in A, I have to show that X naught is in dA. That finishes the story. Well, if X naught is not in A, suppose that is also there. To start with, because X naught is in limiting point, because of X naught is in A bar, for every neighborhood X naught of G, you already know that A intersection G is non-empty. That is coming from X naught being in the closure. But X naught is not in A. Because of this, therefore, A intersection G minus X naught, what is there to remove? X naught is to start with not in A intersection G. This is A intersection G only, because X naught is not in A. And therefore, this A intersection G is only, that is non-empty. And therefore, X naught is in the derived set. So, X naught I take in A bar, either it is in A, if it is not in A, it is in dA. So, every element X naught is either in A or in dA. So, I have proved thus A bar is contained in A. So, I have finished that. Okay. I think we are fine with these things. I'm going to go to another page. I think maybe I have many things to talk about. There is a, maybe I have to talk about all these things. Another page. Okay.
So when we say that A set is closed, do you mean closed set or is the same thing in the previous slide? The second theorem, second part, A set is closed if dA is a subset of A.
Oh, yeah. A is set closed if dA is contained in A. I think that is very clear now. I just realized that if A is closed, then A bar is A in dA. Therefore, dA is contained in. Okay. I need to show that. Well, I can.
No. I mean, when we say A is closed means is it a closed set or like what do you mean by closed?
No, if dA is contained in A. Suppose dA is contained in A. A is also contained in A. So A in dA is contained in A. That is A bar is contained in A. So A bar equal to A. Okay, so
Yeah.
if I have to prove this, we'll prove this here. Proof of 2. What is that? A is closed if and only if dA is contained in A. If dA is contained in A, that is closed. If that is closed, dA is contained in A. So, for example, dA is contained in A. A is already contained in A. So, A union dA is contained in A. But A union dA is A bar. Oh, you know A is already contained in A bar. Therefore, A equal to A bar. Therefore, A is closed. We did a result the other day. A set is closed if its closure is itself. Because if it's closed, it itself is the smallest closure set containing that. If A is closed, A itself is the smallest closure set containing A. So A is A bar. Okay. Conversely, suppose A is closed. Suppose A is closed. Oh, that's also very easy. Then A equal to A bar, but A bar I proved that A union dA. I think that's I'm writing the same thing one more time. Right? If A is closed, A is A bar, but A bar is A union dA, which means dA is contained in A. End of story. So when the limiting points also come into A will be closed. I need to wait a little more time. Later on, we will introduce completeness in topological spaces. That actually clears a lot of things. Actually, you know, I need to do few more things to see that all these things are common sense and nothing more than that. What is the closure of A? Closure of A is other than A, all the limiting points. The limiting points actually in an ordinary sense are obtained as a limit of a sequence of points. In topology, we have not talked about limit of a sequence of a point and so on. In metric spaces, I can talk about it. If I have in a set A, if you look at any point right here, I can reach that point by approximating with points from inside. I can go. I can get a sequence which converges to this x naught, and therefore x naught will be a limiting point. So if I can have a sequence of points converging to some x naught, that idea of convergence will be available to you in metric spaces. I'm still slow in that. In couple of days, in couple of lectures, we will be able to come to completeness. Maybe then everything comes to a complete picture. All right, sir. Okay. Are we fine with this? Okay. Yeah. Two more things I talk about subspace of a topological space. Subspace. XT be a topological space. And I have taken a subset Y of X. And I want to naturally bring a topology on Y. Indeed, it's very easy. So I have this space X, which has topology. That means a lot of open sets are there in this. If I have taken a subset here, this Y is a subset. If I want to create a topology, all I have to do is that intersects the open sets of X with Y. Okay, Ty is of all G intersection Y, where G is an element of the topology of X. It is very easy to see that this Ty is a topology on Y. Very easy to prove that it is a topology on Y. Because the whole space X is also an open set. If I intersect that open set with Y, I get Y. So clearly Y is in Ty. A null set is in T, so null set minus Y is a null set is in Ty. So null set is also in Ty. So the first condition for topology is satisfied. So what I am trying to prove to you is that, okay, here is the little result that says is Ty is a topology on Y. Why is that a topology and why? First thing I told you is Y itself and empty set are both in Ty. Make sense? Okay, because X is an open set in T. X is in T. So X intersection Y is Y only. Y is in Ty. Null set is in T. So null set intersection Y is null set. Null set is in Ty. And it's very easy to see that the arbitrary unions will be. If I take a collection of sets in Ty, they all look like G alpha intersection Y. If I take such a collection, okay, if I take in such a collection and if I want to take their union G alpha intersection Y, alpha in delta, still have to get used to writing easily. G alpha intersection Y, alpha in delta. Oh, this is kind of very easy. It's nothing but union G alpha, alpha in delta intersection Y. Okay, since G alphas are, I'm not writing a very systematically, I should say collection of sets in Ty means they all look like some G alpha into Y. For each subset which is open in this thing is going to be an intersection of open set in T intersection Y. So their union is this, but all these G alphas are open sets in X. Therefore, union G alpha is also open set in X. And therefore, this is open set in X intersection Y is open set in Y, that is in Ty. Okay, is in Ty, Y, since union G alpha, alpha in delta is in T. I think other one is also same thing. If I take finitely many things, finitely many members in Ty look like G1 intersection Y, G2 intersection Y, and so on, some Gn intersection Y. Each member actually, so what is that? I have open sets in X are there and you intersect them with Y, and this becomes, this little thin piece becomes open set in Y. And I take another open set in Y in X and take its intersection with Y, and that becomes, so open sets are intersections of open sets of X. Open sets in Y are intersection of open sets in X with Y. Okay, that becomes a topology. So if these are all in Ty, it is kind of very easy for us to see intersection of all of them. Intersection Gk intersection Y, k equal to 1 to n is nothing but intersection Gk, k equal to 1 to n intersection Y. And of course, finite intersection of open sets in X is an open set in X. So this is in T. And therefore that intersection Y is in Ty, since intersection Gk, k equal to 1 to n is in T. So that way this Ty becomes a topology and Y, and this is called the subspace topology. Okay, and Y is called the topological subspace of the space X5. Okay, Y together with Ty, which is topological space, is called a subspace of X. X comma T subspace of X comma T, but I think I will loosely say Y is a subspace of X. That's all we say usually. Okay. Actually, it's very important for me to have this in my mind. Later on, if I take a subset of a topological space, that subset itself inherits a topology from the full space X. And I might be talking only my all my calculations only on the subset. Then that subset should have a topology, and that topology is this topology. So I have maybe a space here, X, and I might be doing whatever I want to do, the analysis I want to do on this subset Y. So I will no longer go to X. I want to have a topology and Y to discuss everything. And that topology and Y is essentially the topology I have inherited from X. That's what I'm trying to tell you. Okay, we will do that all the time. Perhaps that's fine with that.
Yes, this is very interesting. Basically, this is a constructive approach. So you can create as many topologies as you want by taking a bigger topology and take any subset, and then you can build a new topology out of it, essentially, right?
Every topology on X is going to create a topology on Y.
Right.
Okay,
Right.
that the topology on Y is inheriting the topology of X. So the behavior of the topology of X is going to somehow influence the topology on Y. I can have many topologies on X, as we have seen.
Yeah.
And certain topologies on say NX might, when restricted to Y, might even degenerate to a discrete topology or indiscrete topology. It can be anything. Okay.
So here we are basically, there is a set X, and are we taking the Y from the topology of X, or
Yes.
elements in the topology of X, or are we taking elements of Y in X, right?
Oh, Y
So
should be a subset of X. We want
yeah, Y should be some. Mhm.
only for that. If Y is outside X, it doesn't understand X.
Okay.
Right?
But this Y should also be elements in the topology of X.
Not necessary. Not necessarily. It can be just any subset. If it is also in the a member of the topology NX, you see what happens. If actually this Y happens to be an open set in X, then all the other open sets I take in X and intersect them with G. Suppose Y itself is open, Y itself is some G, then what happens? All the other open sets in X, we bring them and intersects with G, and they will become open sets in X also. So open sets of Y will become open sets in X also. So precisely only the open sets of X which are contained in G, that is Y, become the topology of Y. So here you just proved a little lemma. No, we don't need that. I don't know lemma or proposition. I said I don't need that. What you just said there is that XT is a topological space, and G itself is a member of the topology. Then the topology inherited by G is nothing but all the topological members of T which are contained in G. So I don't get anything new. Same members of the topology will be there. But when this is not a open set in X, the situation will be very different. Lots of things. For example, in C itself, suppose you call this is C, and Y just the curve I have drawn here. And if you take any point and draw a circle around here, and that little thin piece becomes an open set in Y. But that thin piece, which is an open set in Y, is not an open set in C. In C, it is so sparse, it doesn't contain any interior. Okay. Whereas if G is in T, it has some interior in it. G is an open set. Then TG becomes all the open sets of T which are contained in, contained in G. I said it wrong. How is that? Did I answer a question?
Yeah, that makes sense.
Okay. Usually that what happens. Basically, essentially, I have not introduced topology. My plan was is to complex numbers, and so I didn't even make an effort to kind of give a introduction to topology. I realized that we are spending quite a lot of time on it. Topology is in some sense do what? To understand in a space some kind of a nearness. Okay, the nearness is there when you have metric. Without the metric, what is nearness? If there is no metric distance, what is the nearness? Nearness cannot be understood. The nearness is only a neighbor, decided by a neighborhood. The members of the T are the neighborhoods. They may be very big or very small. It doesn't matter. That's all you can really ask for. Okay. So my attempt is eventually to see that that idea of a nearness is used. Once you use the idea of a nearness, continuity arguments will all come. Continuity is all about a function defining on a space X having the property that when X and Y are near each other in the domain space X, Fx and Fy are also near each other. But what is nearness? In topology, I don't have that. Okay. In complex plane, I have metric, I am all fine. So naturally, people will ask, all right, sir, you gave me a topology, quite abstract, quite pathological. Come on, can you give me a metric on it? That means, is this topology inherited from a appropriate metric on that? One will ask that. That means, when such a thing happens, you say the topology is a metrizable topology. Not every topological space is metrizable. So all these ideas will be studied in topology separately. Okay. So anyway, I have a subspace topology given here. You can see that. Maybe I give you one more example for this. So let's take an example. Okay. This is very nice. Z is all real numbers which is contained in R. Okay. R has its own usual topology, right? R has the usual topology. I can say T, that's all, usual topology, which is coming from the metric mod x minus y is distance between x and y. Now, what is the topology that Z inherits? You will be very, very surprised, right? What is the topology that Z inherits? In Z, you have 0, 1, 2, -1, -2, and lots of integers are there. Here is n. You know what?
It's basically this.
Yeah, the
It's
singleton
the intact. Yeah.
can be visualized as the set Z intersection n minus half to n plus half. So n minus half to n plus half is an open set in the usual topology. That intersection has only one element. So every singleton element is an open set in Z in the topology that it inherited. So Z becomes a discrete topology. So all singleton n in Z are open. So Tz is actually going to be discrete topology in Z. Oh, this is very interesting because the original topology on R, if you notice that, I can easily prove that in the original topology in R, every singleton element, whatever you take element X, singleton X is actually closed. Yes or no? Singleton X is closed because R minus singleton X is this minus infinity to
Open.
X union X to infinity. That's an open set. So all singleton
Right.
elements in R are okay. They are actually not open. Singleton elements in R are not open. They're only closed. They're not open because the complement is not closed. So what happened? The behavior of the topology, the usual topology of R inherited by Z seems to have a totally different features. Okay. I hope we understand that. Anyway, we are not interested in talking about all these things. I need to understand a subspace topology because most of the time we look at subsets of the complex plane and our function is defined on those subsets, and therefore naturally it's only on the subset I have to do the business. So I have to look at the topology that is there on the subset. In that sense, I need this one. Okay.
So one question I have, if the topology derived from a Z, right, or Z in this case, is there a way that we can map to a metric topology? I mean, can we define a metric in such a way that TZ can be written as a metric topology?
This is actually metric topology, incidentally. In GR metric topology, same metric seems to be working here. For example,
okay.
Yeah. For example,
right.
What is singleton n? It is the ball with center n and radius half. The Metric is the usual metric. So Z inherits the metric of the R.
R. Okay. Okay.
Okay.
Right. Okay. Okay. Yeah. That essentially it's the same metric that we are bringing into TZ. Yeah. Okay. Makes sense.
Yeah. Okay. What I'm going to do is I just want to spend some time on the metric space CD and RD and understand how some open sets and somehow closed sets look like. What are the limit points? Let's just do a little, set of exercises before I move on to some more ideas. Okay, I'll go to the next one. Okay, first I look at the metric space CD. Okay. It is the usual metric. Usual metric. Okay. I already told you that the topology that I inherit in C, open sets are basically unions of balls, open balls. Okay. So open ball as it is an open. Good. First one I will have is the any open ball for every Z naught in C and R greater than 0, B Z naught R is an open set. It's a basic open set for us really, right? And two, maybe I look at the set A consisting of all those complex numbers such that 0 less than real part of Z less than 1 and 0 less than imaginary part of Z less than 1. So what is that? I have this little box 0, 1, 0, 1. I'm only looking at inside the square. Isn't that an open set?
It is.
Yes, it is, right?
Yeah.
Because no matter what I take an element will be somewhere here, and so you will be able to definitely draw a small enough thing. Indeed, I have written a result here earlier that G is a subset of C is open if and only if for every Z naught in G there exists R greater than 0 such that Z naught belong to B, Z naught R is contained in G. So I think this is open set. No matter what point I take, okay. But the point and the boundary are not used in it. That's why it's an open set. Is open in C. Okay. Is that clear?
Yep.
If I take, for example, A union 1, the point 1, 1, that means 1 plus I. Union the point 1 plus I. So I have included extra apart from this whole thing. I have included just this 1.11 is included. Now, is it an open set? No.
1.
Because whatever small neighborhood I draw, that's not going to be contained inside that. So this is not open. I think openness is very
Plus I. Set,
not open in C. Okay.
set 1 plus I is a closed set. So if you are unioning with a closed set,
It is not
naturally
a
it will
closed set
become.
either. Because there are a lot of points which are on the boundary which are not inside A. This is not closed either. A is neither is A closed nor is A union 1 plus I closed. Neither of the two sets above are closed.
Yeah, there are.
Why is this, for example, why is this not closed? If it is closed, its complement should be open. Its complement, unfortunately, have this one. Unfortunately, have a lot of points. Even 1 1 itself is a bad point. No matter what neighborhood I take around that 1 1, that will not be in the complement. It is for that reason that is not, when you look at A, A is not closed. Why is A not closed? A's complement is involving, you can see that 1 1 is in the A's complement. And any neighborhood of that is not in the complement. Complement is not open.
Yeah.
Same story here also. So they are not closed sets. If you want to say they are closed sets, you have to show that their complements are open.
No, basically what the point I was making is 1 plus I, set 1 plus I, just that set is closed set.
Oh, yes, yes. That set is
right.
closed. That set
So
alone is closed. You are right.
So if
I
I
think,
union a closed set for with any open sets, the whole thing will not be an open set anymore because I'm adding a closed set to it.
Need not be, but sometimes it can be open also. It depends on the topology. It depends on the topology. I have to give you an example, right? So, yeah, open set union singleton, because the singleton is a closed set, you are going to say that open set union a closed set need not be open. I cannot say that. That depends on abstract topologies. If you look at the cofinite topology, suppose X is a finite set, infinite set. Okay, X is endowed with cofinite topology, which means what is this topology? This topology T, cofinite topology, consists of all sets which are subsets of X. Either A is empty, A is the empty set, or its complement is finite.
Yeah.
Suppose I take that. Now, if you take any finite set, set containing, just take one element in that. This is closed because its complement is open. Okay, this is closed. Why? X minus x1 is a set whose complement is finite. Okay, is open because its complement is containing x1. This is an open set. Okay, maybe I even put x1, x2. Okay, that's also a closed set because its complement, which involves whose complement. Oh dear. So we are giving you the example that you are seeking. We'll get that. So set containing x1 comma x2 is closed. Why? Because its complement A, which is x minus x1 comma x2, is open, is in cofinite topology. Because its complement is finite. So it's an open set. Okay? And for that open set A, I have attached just x1.
Okay.
Okay? A is an open set and singleton x1 is closed. For the same reason, is closed. But now this is open. Okay? I have just to use it extra here. This is open. You see that? For an open set, I have attached the closed set. The union is an open set.
Okay. Yeah, it is possible then.
Okay. Well, actually, this is a covariant topology which did that. In the case of a usual topology, maybe a little more comfort is there. We'll see that. So, on the note that you have said, I noticed that for every Z naught in C, singleton Z naught is closed. Okay? Every singleton set is a closed set, right?
Yes. Right.
Why? Even a finite set is a closed set. Indeed, every subset of C is closed. Okay? Every finite subset of C is closed. That's right. Obvious, right?
Yeah. Yeah.
Yeah. Okay. Now I think we can have a feel of what it is. What about Z, infinite set actually? Z as a subset of C, is that closed?
It's a union of a. It's a union of a closed subsets.
But only
But
finite union of closed subsets,
yeah, exactly.
not
Yeah,
arbitrary union.
not arbitrary union. So it and
In the entire C, when you remove it, you just remove the sparse points like this, right?
right.
So any point you take in this space, you can squeeze in an open neighborhood away from all these points, including the points I can take on the real line. I can squeeze in a small neighborhood which is away from all these points. I'm trying to show you the complement of this C minus Z is easily seen to be open.
Open. Yeah, yeah.
Since the case. Is that clear?
Yeah, yeah. So this is one of those cases where I was saying the intersection of infinitely many or non-finite open sets. But when we talk about the definition of topology, we were saying why we are taking an finite, subsets to be closed. But
Yeah.
this is the case where it happens in finite subsets, but it doesn't matter. It's still,
Doesn't,
yeah.
doesn't matter. Doesn't matter. But actually, it's very. I realize that if you really study later on, I'm very sure we'll have an occasion to study. A collection of families which are closed under arbitrary intersection. Also, then you will see that their behavior, that family's behavior, and this family's behavior are totally different. Sir. They're algebras. They're used somewhere else. These are topologies. Topologies and algebras basically like. They're like different people altogether. Their behavior is totally different. Okay. uh, so we have to take our definition like this only, that it's closed under finite intersection. Topology is closed under finite intersection and closed under arbitrary unions. Okay, let's go next page. Some more examples I'll give you about four of them, five. Yeah, I have taken this set to contain, A contains 1 minus 1 by 2, 1 minus 1 by 3, 1 minus 1 by 4, and so on, etc. As a subset of, I can take it as a subset of C or a subset of R. Anyway, subset of C. I want to talk about, is this a closed set? That means is this complement open? That's the question we ask. Is it a closed set?
So if we take its complement, one will be in that, right?
One, okay, I started off with half, then maybe 1 minus 1/3 is 2/3, okay, 3/4. They are somehow,
Yeah.
yes.
Yeah.
Okay, one is actually in the complement.
One is actually in the complement. Yeah. Right.
Okay, and the complement is having problem now. That's not open.
Right.
Okay, because one is in the complement, and no matter what epsilon greater than 0 I take, this 1 minus epsilon to 1 plus epsilon is not going to be contained in C minus A. Okay, I don't, whatever epsilon I take, that's, I'm actually, if A, C minus A has to open, at least I should be able to choose one epsilon greater than 0, so that one is 1 minus epsilon to 1 plus epsilon is contained in C minus A. I'm sorry, we're talking in the complex plane. If that is a complex plane, I will use here B
Ball.
ball 1 epsilon, and that's not going to be contained in C minus A, because in that ball, a whole lot of points in the A are sneaking in.
So somehow this is basically because it is the set is very sparse.
It is
In
actually
C.
accumulating.
Yeah.
At the point 1, and that accumulation is point is not there. This 1 is in the derived set of this A, and somehow 1 is not in A. That's why A is not closed. If you want A to be closed, derived set of A should be inside. All the limit points should be inside A. And
Right.
what is happening is all these things somehow are seeping into 1.1, which is outside. I don't like that. That's the point.
Yeah.
If it's closed, limits should be inside that.
Inside that.
So that is why it is not a closed set. But is it open? Is the next question. It's a sparse set, right? Actually, it's not a sparse set, it's accumulating. It has a limit point. However, whatever point I take in this, suppose I take this, I can squeeze in a small circle around. Is this set open? Did we ask that? No. No, it can be. Right? It's not open. Because that point alone is not in the interior point. It's neither is it.
Yeah.
Okay? Not open either. Sounds good? I think we have kind of an idea how a set will be closed. Set is closed means limiting points should be inside that. The derived set should be a subset of A. We said earlier that A is closed if and only if the derived set A is contained in A. The closure of A is A union the derived set. Okay. One more. What about union B R comma 1 by R? Some silly example I have taken where R is a natural number. Is it inside C? Is it an open set in C or not?
Yeah, it is.
This is open.
Yeah. Each of these balls are open sets. So the whole thing needs
Okay.
to be an open set in A.
Is open in C.
Yeah.
So ridiculous, easy problem there. Okay. And for example, this set in R, AB, I have taken a closed interval AB contained in R. Is it closed or not? Closed interval AB, is it closed or not? So its complement.
Yeah, its complement is open.
Exactly.
Yeah.
So we're done. This is in the usual topology. Okay.
No, it's complement. Yeah, but
It's open.
oh, okay. AB in R.
Okay.
Yeah.
What about one more example I will squeeze in here. Okay. I'm going to take union of closed intervals 1 minus 1 by 2 power k to 1 minus 1 by this is 2 power k to 2 power k plus 1. My writing is poor. Can I'll just go to the next page.
Yeah, let's go to the next.
Okay. Example 8. Okay, which is union interval 1 minus 1 by 2 power k to 1 minus 1 by 2 power k plus 1. K is an integer, natural number, and k is even. So on the number line, I have taken like here is a ball, which is for example, when k is 2, 1 minus 1 by 4 to 1 minus 1 by 8. Then I have gone a little further when k equal to when k equal to 1, when k equal to 1, what is this? That is 1 minus 1 by 2, 1 by 2 to 1 by 2 to 1 by 1 minus 1 by 2 to 1 minus 1 by 4. Okay, I think that has encroached this. Yeah, that's not a problem. You can say k is even and k is greater than 1. Nothing wrong if I include that. Nothing wrong if I include that. Just avoid that for a minute. Not a big deal. Okay, so starting from 2. So this is the first set. When you put k equal to 3, I have 1 minus 1 by 8. Not k equal to 3, k equal to 4 is what I put. K equal to 4, I got 1 minus 1 by 16 to 1 minus 1 by 32. So I just wanted to have a little space between the two things. And like that, I think I have taken lots and lots of intervals. I am not able, I cannot really show them all, right? And so on, right? One is somewhere out here. Now, what about this arbitrary union? Each is a closure set I have, but arbitrary union need not be a closure set. Is it a closure set?
All the complements are open, but
Yes.
their intersection, because it's an arbitrary union, their intersection may not be open.
Yeah.
I don't know. So I can't use that argument. Yeah.
Actually, what I'm doing these sets are slowly, some points in these sets are converging to the point 1.
Yeah.
And that 1 is not in that set. So
that's a limit point, which is not in that set.
1 is in the derived set of A, but not in A. That's the problem. Okay, that's why it is not closed. Okay, sounds good.
Yep.
All right. I don't know. How are we on time? Oh, already 11:30, brother.
Yeah.
I'm kind of going slow. I have a lot more planned in it. So maybe I better stop after answering some of your questions. What I have to do is beyond that is connectedness. I will talk about it tomorrow. Maybe I leave with one definition. Okay, give me a couple of minutes. One problem and one definition. One more 9. Q of rational numbers, set of all rational numbers inside R. Okay, what is Q bar? The closure of Q. For example, closure of Q is nothing but a Q union the derived set of Q, right?
Right.
Derived set of Q is in some sense limiting points are all in put in that side.
Right.
Now every real number is limit of a sequence of rational numbers.
That becomes real itself. Yeah.
So that's why every real number sneaks into DQ, and so therefore Q bar becomes the entire real line. Okay.
Yeah.
Here is a definition. Suppose I have a topological space XT. Okay. a subset A of X is said to be dense, is said to be dense in X, or is said to be dense if A bar is equal to X. Just it encroaches the whole X. It's dense in X. Everywhere the points of A are there in X. So whatever other element you take in X, there is a sequence of elements in A which somehow close in on that point X. See, I have not talked about sequence of things in topology, and I cannot talk about it. But if I keep in the metric space into account, I think I have to do the completeness very soon. It is very clear what is happening when you say it is dense in X. That means every element of X is encroached by elements of A. That's why A is called dense in X. Right?
Mm.
And a topological space is said to be separable. A topological space is said to be separable if it has a countable dense subset. If it has a countable dense subset. Right here, this Q is a set of all rational numbers is a countable set, and it's dense in R. So R is called a separable topological space. Actually, it's metric space, separable metric space.
So all these things you can only so when you can talk about countable subsets irrespective of whether it is a metric space or not. Okay. Yeah.
So in that case, R is separable. Q is a countable dense set. Countable dense
subset of R.
So therefore, R is a separable metric space. R is a separable metric space. Separable topological space. In this case, it's a metric space. Okay, separable topological space. And I think it's very easy for us to see that even C has that property. In C, I can introduce a set A, which is all A plus IB, where A and B are rational numbers. You can see that E is dense in C.
Yeah.
Even C is separable. Even C is a separable topological space.
Yeah.
I think with that, I would like to close. I will answer any questions you have. For today, if I stop here, in the next class, I think we can have the next class tomorrow. We will talk about the connectedness of a topological space. We have to talk about that. And the next, we have to talk about completeness of a topological space and then compactness of a topological space. 3 more ideas we have to talk about before I stop my introduction of topology for complex function theory. If you have any questions, please go ahead.
No, I think this is good. It takes some time. I'll have to go back and look at all the notes again, and it's getting a little bit overwhelming, but I need to go back and go through all that again to kind of settle down.
Okay.
Yeah.
Before Monday, I try to see if I can write all the notes that I have done. Actually, having a concrete lecture notes will be very easy. I'm actually, you know what, out of rush. I'm just coming and talking without really writing much on my own. Some scribble, something there, and I'm talking about it. I will write the notes up. 3 lectures, right? It's not a big thing. I'll send it to you. Then it becomes a little easy. We will slowly, after looking at a lot of examples, we get a grip of what it is. And once you have topology, then I can start my complex function theory. There are ways in which I can just teach complex function theory without referring to any topology. We can really do that. If basic complex analysis, I think that I can introduce for people with nothing more, can be taught without any of these things. But the richness of the complex function theory uh, can be appreciated only through ample amount of topology. Okay, that's all for now, and we'll have a class tomorrow.
Okay.
Same time.
That's good. All right.
You have a good day. Bye
Yeah.
bye.
Thank you. Thank you very much.